Okay, for this tutorial on using Excel to graph and plot data and do some curve fitting, you'll be using Microsoft Excel. I'm using the Macintosh version. You may end up having a Microsoft version, PC version that you'll be using. So some of the things may not look exactly the same. The idea behind this is to get you used to using a very professional looking graph routine that Microsoft Excel provides for you. It just takes a little bit of getting used to. If you've used Excel before, you will relearn it very quickly. If you haven't used these data graphing and curve fitting relationships that it provides, well, this is your opportunity to get up to speed. When you're done, you're going to end up with something that looks like this page. You're going to have your data, you're going to have your calculations, and you're going to have your chart with all the proper labels and relationships on it for you to import into the lab. In this tutorial then on graphing, we'll examine data taken from an experiment in which the circumferences and radii of several circular objects were measured. So you're given the data over here from a fictitious measurement here that was used to calculate the value of pi. The equation associated with this data, the circumference is equal to 2 pi times the radius, then is used. C equals 2 pi r. In this experiment, the circumferences and radii then were measured, and when they were captured into this array on the chart. We hope then to be able to determine the value of pi for which a 6 significant figure value is given, 3.14159. Here we show how to use Excel to plot the data. To do so, follow the steps. It may appear that this is a difficult process, but it's really rather straightforward and simple. So you're going to create an array on your blank page, your blank spreadsheet, and from that, Excel is going to draw the graph for you. So enter the data, as you see here, into your blank worksheet given in the screenshot. Use the insert symbol to enter the value of pi. I don't want to see pi type there. I want you to use the symbol. So you can enter your title as calculation of Greek letter pi on the page. Click on an empty cell within the worksheet and then click the Insert tab from the toolbar. So you see over here on the left side, Insert. When you do, you're going to see the choice that you're looking for as Scatter. Okay, this gives us points, not lines, nothing connected in your graph. So you will highlight your data, not the titles, just the data in your array, and then when you click on the scatter function, Excel is going to build your graph for you. Okay, so the chart type window will open. Choose the scatter option. Do not select any of the subtypes that connects your data points together with lines or curves. We're going to do something called a best fit or a trend line to overlay across the top of your data. Okay, so no selection of the subforms. So now as soon as you do that, you can see you still have your data up in the upper left corner, but now on the top of your spreadsheet you actually have your graph that was just plotted by Excel. You see the units on the X and Y axes, and then the dots that are put on the graph itself for your data. You'll notice on the right hand side there's something called Series 1. We don't need that. We're going to delete that later. All that's telling you is that series is the XY relationships for your data. It becomes superfluous for what we are doing in the labs. So from the Layout tab now, you're going to choose the Label menus to add or edit information on the graph chart. So you can see on there lots of choices: chart title, axis titles, a legend, data labels, axis, grid lines. Okay, so by selecting layout, all those become available to you and are the tools that we will use to start labeling this graph and a chart. As I said before, since you're not going to connect your dots together, we're going to use something called the trend line or the best fit. You should always add a trend line to the graph. That is, make the computer draw the best fit line for your data. So it's going to do an approximation and say, okay, if these were connected and all on the line, they would look something like this. As you can tell, there's going to be some amount of error there, and that is going to be calculated by Excel. Always add the trend line to the graph. That is, make the computer draw the best fit line for the data. You should also display the equation and the R-squared value to the graph. So you'll notice here you're going to select linear trend line. That's the only one we will ever use for this course. We will also then on the bottom select more trend line options. When you select more trend line options, what comes up are those two values that we're looking to add to the graph. Display equation on the chart, check. Display R-squared value on the chart, check. Since the relationship then between the circumference and the radius is a linear relationship, we can expect the plotted data to form a straight line of the form. You should remember this from your algebra classes, y equals mx plus b, okay? Where m is the slope of the line, y then is your array of data points, x is your array of data points, and b is the y-intercept. You will always delete the plus b because it generally will not be crossing the y-axis. To add the trend line, click anywhere on the graph and then click on the Chart Add Trend Line from the menu bar. Since we expect the fit to be linear, select the linear fit. To display the equation in R-squared value on the graph, click the More Trend Line options, then place check marks in the appropriate boxes. So that's going to automatically do that for us on our graph. Okay. It is possible with Excel to add trend lines other than linear ones. For example, logarithmic, exponential, polynomial, power series, or a moving average, depending on what you're looking for. We will never be selecting those other options for what we're doing in our labs. There will always be a linear relationship. So, when the OK button is pressed and the best fit line is drawn, the equation of the line and the R-squared value will be displayed on the graph. It'll look something like the screenshot that you see. You may move the equation by clicking and dragging it to the desired location. So you'll notice here when you clicked on it, your R-squared value, the square of the correlation coefficient, and your full y equals mx plus b. As I said before, you're going to delete the plus b part. You'll notice that we have y and x here. We don't have any y or x in our graph, so you're going to have to change those. And then you're going to delete this legend series 1. The R-squared value is actually the square of the correlation coefficient. The correlation coefficient, R, gives us a measure of reliability of the linear relationship between x and y values. The value of R equal to 1, which you probably will never get, indicates an exact linear relationship between your x and y values. Values of R close to 1 indicate excellent linear reliability. If the correlation coefficient is relatively far away from 1, then the predictions based on that linear relationship, y equals mx plus b, will be less reliable. If it's way far away, you should notice your points not lying very close to your trend line or your best fit line. You should find it odd then in the previous equation where we had y equals 6.179x plus 0.02327. The odd thing that you should notice is that we don't have a y and we don't have an x. We have the representation of the x and y axis, but our x and y axis is labeled C and R for circumference and radius. After all, we did not measure at y's and x's, but rather circumferences and radii. You should always then change the displayed equation to match your measured variables. To change the equation, simply click on the equation, change the variables. The screenshot then shows how we made our equation more representative to the experiment. Recall that the governing equation for this experiment was C equals 2 pi times R. C is equal to y, R is equal to x. 2 pi then becomes our slope of the line. So now you can see when we change those variables, deleted the y-intercept, we have exactly what we're looking for. Our relationship and our correlation coefficient. The series is still on here. We're going to remove that. So by doing this step, you are in essence telling me that you really do understand what was actually measured and how well the experiment matched the theory. A nice touch to your graph is also to decrease the thickness of the best fit line. That's that line connecting the points, sorta. The default size is rather thick and often hides the actual data points. To make the line thinner, double click on the trend line and change its weight to a thinner line. The final result of your efforts is a graph then that looks something like the following. Notice it has a nice title on there, calculation of pi. Notice it has nice x and y axis labels that we changed and identified them as circumference in centimeters, radius in centimeters, always add the units. We put our equations on the graph and we got rid of the series markers. Simply making the graph is not all that's required of the physics student. The real job of the physics student is to determine what physics principles, if any, were verified by the laboratory experiment. You must constantly ask yourself, what physics principle was the experiment designed to show? And did the experiment actually verify the theory? So in this example then, we hoped to show that if we plotted the circumferences of several circles versus their radii, the slope of the resulting graph should equal 2 pi. We have a very nice graph, but we've not determined if the experiment actually verified the formula circumference is equal to 2 pi times the radius. You should expect by now that we can use Excel to compare the experimental slope to the theoretical slope. Another way of stating this is, what is our experimental value of pi? The screenshot shows us how to use Excel to do this. Our slope was determined to be 6.179. No units, right? The theoretical value of the slope is equal to 2 pi, or moving our terms around, pi is equal to the slope divided by 2. The formula in the cell F4 gives us the value in the cell F2 divided by 3. Okay? This gives us the experimental value of pi to be 3.09. The formula in cell F5 gives us the percent error between the actual and experimental values. As you can see, an error of only 1.66 indicates that the student performed this lab very carefully. 166 is not a bad error. Note that in our percent error formula, cell E4 above did not explicitly multiply by 100%. Instead, we let the power of Excel calculate the fraction, and we clicked percent style to add the percentage to the relationship. Once again, ask your professor if your graphs should be on separate pages or included in the data table as shown. Make sure that when you print your results, you print grid lines and row and column headings. Make it look professional. So when you're done, you should have something that looks like this: your array of data, your array of calculations, and your final graph and chart. So good luck with this. The idea behind this is to make it a learning experience. If you have to, go into YouTube and try to find some other tutorials that'll help you if this one didn't help you. Everything is a learning experience, and the best way for you to learn it really is to dig out the information yourself. Thank you.